Thank you everybody for listening our presentation. And the topic is learning from interpretation transition using differentiable logic program semantics. And before describing our model, we would like to show some background. And the normal logic program is a finished set of rules that satisfy the following form. And we can see LR are the literal and H is the head order. And give a logic program P, the set of order in P is called Herbrand base, and we also denote that BP. And an interpretation logic program is a subset of BP. And we can regard the interpretation as a state to show the current literal are true in the logic program. And the interpretation vector can represent interpretation, and we can define in this embedding. And we also show the immediate consequence operator. This operator is a function from interpretation to another interpretation. And we can, if we use this kind of definition to calculate the next state given the current state. And we define our learning task as following. So we will learn a logic program from a lot of pairs of interpretation transitions and I and J, where J equals to TPI. In our model, we use two different steps to learn symbolic logic programs. And the first step is meta-info learner, and the second step is interpretation learner. The connection between two learners is that the meta-info learner generates meta information. This kind of information will reduce the search space for the interpretation learner. In the final step, we can extract the symbolic rules from interpretation learner. We first give a method about how to embed in the normal matrix given any normal logic program. We want to meet this kind of formula, that means the normal matrix product the input interpretation, and after a state function, we can get the output interpretation. The state function can define as follows. And we use this kind of embedding method. There is a very explicit example. If we have a logic program have three different rows, which had variable R, P, Q, and R, and then we have three different rows in a normal matrix. And we have totally 6 different literals in the logic program. They are P, Q, R, and negative P, negative Q, R, negative R. So we have 6 different columns in the normal matrix. And for the first element, well, how we calculate, because the denominator of this friction corresponding the literal P is the number of the literal in the conjunctive class with the least literals that appear in the corresponding row. We can see the variable P in this row, the P and the negative Q only have 2 different literals. So the value of this position would be 1.5. Similarly, we can calculate other values in the rest of the position. We can see the number of non-zero elements in each line equals the number of different literals in the corresponding row. In the next stage, we want to use a differentiable function phi to replace the function theta, because we want to use a neural network to learn this matrix to get some meta information. And we can see we use this function to replace the theta function. The larger alpha and the function theta and the function phi x minus 1 will be more similar. So alpha is a hyperparameter. And in the next, we just imply this equation to emit the to infer like immediate operator, immediate consequence operator, and use this function as a loss function, where H is the cross entropy loss function, and the second term is penantator. In this stage, we will use the non-zero elements in every line and denote as LPK from generate normal matrix as meta information. So we have LP equals to 4 and etc. In the second learner, we just in the first learner we learn how many different leaders in the different logic rules with different head variables. And in the second stage, we want to know what kind of symbolic form for each for different logic rules with different head variables. So before do that, we want to give a proposition that is the number of rules M in a same head variable logic program is no larger than this number. This is a combination number. The same head variable logic program is just like the logic program, and each rule have the same head variable. And we can see in the interpreter learner, we just use the learn same head variable matrix to representing the case rule in the disjunctive normal form logic program. And there is another example to show the learning process in the second stage. Actually, we set multiple trainable matrix MPSHV to represent different disjunctive normal form rules in the logic program. This embedding method is similar with the last one, but because this kind of same head variable logic program is much easier than the last one. So we just the denominator of the function corresponding the literal P is the number of literals in a corresponding rule. We use this kind of embedding and to product input interpretation after the active function we defined before the find function, and we got 3 different output value for variable P, and the logic program, the Boolean value of variable P after fuzzy R operator, we got the final Boolean value for the variable P. And this is the inference formula to replace the immediate operator, consequence operator. The last function in this stage is similar with the last one, but we add another constraint. This constraint just constrain the sum of each line of the SH matrix to 1. There is another example to show our learning process. We can see this rule have 2 different rows in their corresponding SHV logic program. So we use 2 rows in the SH matrix. In the next stage, we want to learn the first order logic program from the relational database. In order to perform this task, we need to adopt the bottom class propositionalization algorithm. This algorithm just transfer the relational data to attribute value data. After apply this algorithm, we can generate a lot of bottom classes. We can regard the bottom classes as propositional logic program and make the first order features as propositional variables. In the next step, we generate pairs of interpretation transitions according to the bottom class. there is an example to show how to use our model to learn first order logic program. If we have three sets, the facts are mother, wife, and wife relation, and the positive target and negative target. And we have mom one, doctor one, so many different objects. Based on three sets, we apply bottom propositionalization algorithm, and we will generate two bottom classes. The first one is that we can base this bottom classes set and generate pairs of interpretation transitions. I1 and G1 is actually I1 is a body of first order features in the first bottom class, and the G1 is the head first order feature in the first class. Because the second class, the head of the second class are with negation, so we just use an empty set to regard the output interpretation. We also conduct some experiment in incomplete and mislabeled data set. We test the accuracy of logic program and the MSE compute by the neural network. We also compare the result with alpha IT and alpha 1T and G-RAPE on several propositional data sets and relational data sets. This is some result. We can see that our model are comparable with alpha IT and alpha 1T and CLP++. In conclusion, we just show that the alpha IT is a neural inductive logic programming learner based on the neural network, and it can learn mislabeled data or incomplete data to generate the propositional logic program. And through adopting the BCP program algorithm, we can also learn first order logic programs from the relational data set. And we can also use curriculum learning strategy to learn the knowledge, because the learning trainable matrix is very flexible and easy to operate. So in the future, we will devise more constraints to make the generative logic program to meet some formats, apply the model to the knowledge graph. Thank you for your attention. Thank you.
Thank you very much. Are there any questions? In your last slide, you mentioned that you want to devise some constraints in order to meet some formats in the penultimate bullet point. Can you give some comments about this? What do you mean by destined formats?
You mean curriculum learning strategy is just learn some logic program, and after we got some logic program, we can use this knowledge as a period knowledge, and the embedding of the logic program is very easy because we have described the embedding method. So we can transfer the symbolic logic program into the matrix to, if we generate the 100, the correct logic program, we can fix the corresponding value in the matrix. Then we can continue to reduce the search space to improve the accuracy. Yeah.
Thank you.
So yeah, thank you.